Welcome back everyone, Houston Math Prep here to go over the second derivative test for functions of two variables and finding local maxima and minima. If we assume we call some point P, and that's in an open region of the domain of our function f of x, y, our point P is a local max if you could not walk uphill on the graph immediately in any direction from P. If you look at being at the top of this hill, let's say on the z-axis, obviously there's nowhere to walk but down in any direction. So that's the idea of a local maximum. Additionally then, point P is going to be a local minimum on the graph if you could not walk downhill immediately. In other words, you could only walk uphill no matter which direction you go. So think about still being on the z-axis here, but now we're at the very bottom point of this valley. Doesn't matter which direction we face and then start to walk from the point we're located, we're always going to be walking upward. So since we can only walk upward, can't walk downhill, then this is a local minimum on our graph. If you think back to single variable calculus when we just had a function of x and we wanted to figure out where the local extrema were, what we did was we took the first derivative of our function, we figured out where that was 0 or undefined at some x values, and those x values were considered to be a critical value, a critical point for our function f of x. Remember that when you had a critical point, we then checked to see if it was a local max or min. It was not guaranteed to be a local max or min, but it was a candidate for a local max or min on our function. One thing that we want to remember for a local max or min is that this x value really needed to be an interior point. In other words, if you were just looking over some closed interval, it was not an end point. It was actually an interior point, a point in the middle of your interval somewhere. And remember, once we found our critical points on f of x, then we used some combo perhaps of first and second derivative tests to determine if something was a max, whether it was a local min, or whether it was neither one. So for functions of more than one variable, we want to look for points in the xy plane that are in the interior of the domain for our function. And we will look specifically where our first partial derivatives, partial derivative with respect to x and partial derivative with respect to y, are both 0, or at least one of these partial derivatives is undefined. Those will be our critical points. Now let's just look at quickly what we mean about interior when we talk about a function of x and y. Here I have an upper hemisphere, and if we want to think about the interior of fxy, let's say we give this function a formula. Let's say we give it that our function is equal to the square root of 36 minus x squared minus y squared. So that's our equation for this upper hemisphere. Its radius is 6, if you can tell by looking at the formula. So if we look at the domain, in other words, where in the xy plane do I have graph above that? Anywhere on a circle of radius 6 or inside of it, we are going to have graph above that point if we look vertically from the xy plane. Now, if we want to be on the interior, that means I can't be on the edge of this region. So that means actually our interior is just going to be when we are inside the circle of radius 6, not on the edge. So our interior is considered to be x squared plus y squared, just less than 36 in this case here. Now, it may be obvious for that hemisphere that we just looked at, but let's say we want to find the critical points and just test an easy value that we should be able to look back at the graph and say, we expected this to be a critical point. So we have our hemisphere equation, the square root of 36 minus x squared minus y squared. And remember that we can think of this as 36 minus x squared minus y squared, all to the 1/2 power. And that may make it easier for us to do our partial derivatives. So remember, we'll have to figure out when these partial derivatives are both 0 or one of them is undefined. So we'll look at partial fx. So power rule, the 1/2 will come out front. We won't touch the inside stuff, so we'll leave 36 minus x squared minus y squared. To the power goes down by 1, so that will be to the negative 1/2 power. And then the derivative of the inside will give us that will multiply by negative 2x, taking the partial derivative with respect to x. So for this one here, the 2 and the 1/2 cancel, so we get negative x over the square root of 36 minus x squared minus y squared. A similar thing is going to happen for fy. Partial fy, the 1/2 would come out. We wouldn't change the inside stuff. We'd have 36 minus x squared minus y squared to the negative 1/2 if the power goes down by 1. And now the chain rule would give us a negative 2y from the inside. And so we would actually get the 2.5 reducing again and get negative y over the square root of 36 minus x squared minus y squared. Now, if we're looking for places where this is 0 or where it's undefined, we can go ahead and do that. So f of x will be equal to 0 when, since we have a fraction for this expression, the way for a fraction to be 0 is when the top is 0, as long as the bottom is defined. So the top will be 0 exactly when x equals 0. And if we look at when is fy equals 0, well, fy equals 0, same thing. We have a fraction, and so a fraction will be 0 when the top is 0. So when y equals 0, then we will have fy equals 0. So we have partial fx equals 0 when x is 0, and partial fy equals 0 when y is 0. And where are they both 0? Well, that would have to be at the case 0, 0. So when we are above the origin in the xy plane, we have a critical point on our function. And if you look back at our graph of the upper hemisphere and think about a point above 0, 0, which was our critical point, no matter where I walk in any direction along the hemisphere, at that point I'm going to be going down. So while we don't know yet from a derivative test how to figure this out analytically, looking at the graph, we can see that this would be definitely a local max at that point, that critical point would be. We do have, it turns out, a second derivative test for functions of x and y. It helps us classify critical points as local max or local min. However, with functions of x and y, there is another possibility just besides being a local max or min, or saying we get some sort of failure of a test. It's possible that we have something called a saddle point when we have functions of both x and y. A saddle point is some point p that's a critical point, and basically the idea is at that point p, if I look certain directions on my surface, on my graph of f of xy, I could walk uphill, and certain directions, if I walked immediately, I could go downhill. The easiest way to see this, I think, is probably to look at a classic graph that you've probably already seen, a hyperbolic paraboloid. We'll have our function of xy equal to x squared minus y squared. So here I have the graph of this. If you can tell already by looking at it, if I'm at this central point here, you might notice that there are some directions I can walk uphill and some directions I can walk downhill. Let's look along the axes especially. If I look along the y-axis and I think about somebody walking this surface above the x-axis, so they're walking this direction, you can see that this point here, this central point at 0, 0, is actually a minimum if I look this direction. But if I turn and I look down the x-axis straight on, you can see if somebody was walking below the y-axis, this would actually be their maximum point as they were walking along the graph in this direction. We're able to look up certain directions on the graph from a certain point, and we're also able to look down in certain directions from that same point. Let's go ahead and look at our second derivative test for these to determine when something's a local max or min or perhaps a saddle. So we're going to assume that p is some critical point, and we're going to assume that the following derivatives in our test are all continuous and we don't have any problems with those derivatives. Nothing weird is going on at our critical point with the derivatives. So we're going to evaluate this object. We're going to call it D. D is going to be equal to the determinant of this 2x2 matrix that has all of the second partial derivatives in it in this particular order. So you have fxx, fxy, fyx, and then fyy. And we're going to evaluate this at the point P. So remember, to evaluate a 2x2 determinant, we take the main diagonal and multiply, and then we will subtract what we get on the other diagonal multiply. So we'll have fxx times fyy minus fxy times fyx. And remember, as long as we have functions that are very well behaved, most functions are going to fit the criteria that these mixed partial derivatives, fxy and fyx, are going to be the same amount. So we can really think of this as fxx times fyy minus one of these mixed partials squared. How we'll use D to evaluate whether we have a local max, local min, or a saddle. So our first criteria, if D ends up being a negative number, then our critical point is a saddle point, right? We have some directions where we have higher points and some directions we have lower points. That's a saddle point. When our D is positive, there's two possibilities. If D is positive and our pure second derivatives are greater than 0, then we'll have that our critical point is a local minimum. If our D is a positive number and our pure second derivatives are negative, then P will be a local max. Our critical point will be a local max. It also turns out in this second derivative test, just like another, if D equals 0 for this one, we actually get that the test is inconclusive for us. Also, just a little tidbit, this matrix with all second derivative entries in it, that's called the Hessian matrix. Okay, so I think it's pretty clear. If we get a negative value for D, it's a saddle. If it's positive, we get one of the others. We get a local max or min. Let's look at the difference in these scenarios. If D is positive and our pure second partials are positive, we get a local min. Think about what's happening there. If I'm walking along the x-axis, I'm walking above that, so I'm only changing in the x direction, and fxx will tell us about concavity in the x direction only. So if it's positive concavity, that means at this critical point, we are actually concave up, so we're bending upward as we think through this point in the x direction. The same thing will be true for the y direction. If fyy is positive, then that means we will be concave up in the y direction as well. And so you can probably see here, if we're concave up both directions from these points, then that's going to be a bottom point. We're bending upward from that point, and bending upward from a point will make that a local minimum. The other way is true for the other one. If we have negative second pure derivatives, and we look through the point in the x direction, then we will be concave down, and similarly in the y direction, we will also be concave down, looking just in the y direction through that point. So because we're bending downward in those directions from this point, then this must be a local maximum. So let's work through a couple of examples here. We want to find and classify all critical points of our function x cubed minus 3x minus y squared plus 4y. So we'll first find our critical points. We will find our first partial derivatives and figure out when those are both 0. So partial fx is going to equal 3x squared minus 3. And for partial fy will be negative 2y plus 4. Now we want both of these to be 0, so we need to figure out when both are 0. So when is partial fx 0? Well, we'll just set that equal to 0. So 0 equals 3x squared minus 3. I could go ahead and, I guess, divide both sides by 3. So we'll say 0 is equal to x squared minus 1. I could factor this or move the 1 to the other side and then take the square root. So here we would get that x is equal to positive or negative 1. And that will be when partial fx is 0. To look at when partial fy is 0, I need to set this equal to 0. So I would say 0 equals negative 2y plus 4. If I move the y term to the other side, we would get 2y equals 4, and then dividing by 2 gives us that y equals 2. Now, we need both of these things to be true for a point to be a critical point. So I could have positive 1 and positive 2. That would be a critical point. And then I could also have negative 1 and positive 2, and that would also be a critical point. So these are my critical points. Go ahead and say critical points are 1, 2 and negative 1, 2. Now we want to classify these using our second derivative test. Remember, our second derivative test will be the determinant of the matrix second derivative with respect to x. We have our mixed partials, and we have fyy down in the corner. Well, my fxx would be the derivative of the fx that I already have with respect to x. So taking the derivative of this with respect to x is going to give us 6x there. fxy, if I take fx and take the derivative with respect to y, I get 0. fyx, you're going to see we get the same thing. If I take fy and I take the derivative with respect to x, I get 0 because there are no x terms there. And then fyy, I'm taking fy, and just the derivative with respect to y there is going to be negative 2. So we go ahead and take the determinant here. If I take 6x times negative 2, that will give me negative 12x minus 0 times 0. So I just get negative 12x. And now I need to plug my critical points into this formula for D to see what I get at each one, and that will tell me what things are. So if I plug in the positive 1, positive 2 into that, then that's just going to give me a place to put in x only. So that's going to give me negative 12. Now, if I get that D is negative, remember, that's going to tell us that something is a saddle. So that tells us that this 1, 2 as a critical point is actually a saddle point. Let's look at the next one. Here we have negative 1, 2. So if I plug in negative 1, 2 into my negative 12x, well, that's going to give me negative 12 times negative 1. I'll get a positive 12. So my D is positive. So that means this is a case where I get a max or I get a min. And remember, the way we do this is we look at the sign of the pure second derivatives. So let's think about the sign of the pure second derivatives. If we are at -1, 2, if I plug that in to this first one here, that's going to give me a -6. And so I will have a -6 and a -2, and those will be the signs for my pure second derivatives. These are negative. In other words, they're less than 0. So that means the concavity at this point in both directions is down. Negative would mean we're concave down. If we are concave down, bending downward from a point, but we have a point and we are concave down, then that means that this point will be a maximum. So we have a local maximum at -1, 2. Okay, looking at another example, we want to find and classify all the critical points of our function x squared minus x squared y plus 2y squared. So we'll do the same thing. First, we'll figure out our fx. So partial derivative with respect to x is going to be 2x minus 2xy. And if we figure out our partial fy, that would be 0 for the first term. We'll get -x squared plus 4y for partial fy. All right, let's go back to where partial fx equals 0. Let's figure out when that happens. So if I set this equal to 0, I will get 2x minus 2xy equals 0. I could factor out a common 2x here. So I could say 2x times the quantity 1 minus y equals 0. And then that's going to be true when 2x equals 0, in other words, when x equals 0, or when 1 minus y equals 0, and that's going to be true when y equals 1. Let's look over here. Partial fy equals 0. That would give us 0 equals -x squared plus 4y. So that then tells us that x squared is equal to 4y. Now, I can't really solve this by itself, but I know that this has to be true. So x equals 0 is a possibility. If I plug in x equals 0 over here, then that would give me that 0 is equal to 4y, and then that would tell me, obviously, that y has to be 0, right? So when I plugged in x equals 0, I got that y equals 0. So one of my critical points for this is going to be the origin, 0, 0. If I look at the other condition that makes this one true, which was y equal to 1, and I plug that in, then I get x squared is equal to 4 times 1, which would be 4. And now there are two possible cases for this. Square rooting both sides, we would get that x equals plus or minus 2. So when y is 1, x could be 2 or -2. So we also get critical points 2, 1, and -2. 1. When I plugged in 0, I got 0 for y. When I plugged in 1 for y, I got 2 and -2 for x. So these are our three critical points here. Now we'll use our second derivative test to determine what they are. So let's go back and find d. So d is going to be our determinant with the second partial derivative. So we'll have fxx, fxy, fyx, and fyy, and we'll take the determinant of that matrix. Okay, so fxx, partial derivative with respect to x, take it with respect to x again, then we will get 2 minus 2y. fxy, if I take the derivative of this with respect to y, I will just get -2x. Let's just make sure we did it correctly. If I took the derivative of fy with respect to x, I would also get -2x. And fyy, we want to take fy and take the derivative with respect to y again, and that would just give us 4. If we take this determinant, if I take 2 minus 2y times 4, that will give us 8 minus 8y. And then subtract this diagonal multiplied. If we subtract that diagonal, then that will be 4x squared. So we have 8 minus 8y minus 4x squared. We go ahead and plug in our points here, and we'll see what we get. So if we plug in 0, 0 in this one, then we'll get nothing for this term or this term. That will give us +8. Okay, when we get something positive, that means it's a max or a min. So this is a max or a min for 0, 0. And the way we tell is to look at the signs of the pure second derivatives, right? You can already tell that fyy is positive here, right? But you can see if we plug in 0 in here, you'll get 2 minus 0, and this will be positive as well. So you get positive 2 and positive 4. So our pure second derivatives are positive. So that means from this point 0, 0, positive second derivative is concave up. So we're bending up. And if we're bending up from a point, then that would make it the minimum. So this is a local min for our 0, 0. Now think about plugging in 2, 1 into our determinant. So if we plug in 2, 1, plugging in 2 for x and 1 for y. If I plug in 1 for y, that will be 8, and 8 minus 8 will be 0. And if I plug in 2 here, I would get 4 if I square that, and then times negative 4. So that's going to give us negative 16. And since d is negative, we know that this is one of the cases where it's a saddle point. So 2, 1 is a saddle point on the graph. And if we look at negative 2, 1, perhaps a similar thing happens, right? If I plug in negative 2, 1, well, the 1 for y still makes this 0. I'd have 8 minus 8. When I square negative 2, I'll still get a positive 4, and then multiply by negative 4 is still going to give me a negative 16. So it turns out that this point is also a saddle. So we can certainly have more than one of any kind of these, or we may have none, right? This one has no local max. All right, everyone, hopefully this gives you a good idea of how to determine something is a min or a max locally, or it's a saddle point, finding your critical points using the second derivative test. Thanks for watching. Good luck with these. We'll see you in a future video.